Hello friends, so today we are going to solve 3 questions, and these 3 questions are from our conservation of energy, conservation of momentum, and the last one will be from your, you can say, center of mass thing, because it is somewhat related to the second question. The basic question is same, but the method of solution will be entirely different. So we start from the first question, and it states that a roller coaster car starts at rest and coasts down a frictionless track. It encounters a vertical loop of radius r. How much higher than the top of the loop must the car start if it to remain in contact with the track at all the times? So we can draw the basic figure. So it means the car encounters a vertical loop. So let us make a vertical loop, and this is some, doesn't look like a loop. So let me make a circle, okay. And so this will be some kind of loop. And it starts from the rest from a certain height. Okay, so let us make a height, and this is our horizontal level. Okay. And it states that this vertical loop is having a radius r. So this is the radius r of the loop, and so total height of this loop, which will be nothing but diameter, so that will be 2r. And let us say it starts from point A, okay, and the vertical height of this point A from the base is, let us suppose, is our h. Okay. And it says that how much higher than the top of the loop. Okay, so it means we are interested in finding out this height, which we can easily find out because we know this distance is about 2r, so we can find out this. Okay, so let us find out h, and based on this we can easily find out what will be the height above the loop. And so in this loop, let us mark one point. Let us call this point as B, and we are mainly interested in this point B, okay, because if the car or the vehicle is able to maintain the contact at this point B, it will be able to maintain the contact at all the points, okay, because in this case the mg as well as normal will be acting both in the downward direction. Okay. And so we are going to consider this point B, and so for this point B we can just draw it separately also. So this is our point B, and this is the base. So the height of point B is over 2r. So this is point B, and at this point B we are having a normal in the downward direction as well as our mg also in the downward direction. Okay. So this is the most of a critical point that is our B. So we are going to find out the condition for the contact at the top of the loop. Top of the loop means at point B. So you can see condition for contact at the top of the loop. and in this case the vehicle is going to start from A and it will be traveling like this, and ultimately it will be going back. So it means for this top of the loop means point B, and point B we can write the equation that our normal plus our mg will be giving us our the radial force balance, that is our mv square upon r. Okay. And for just contact, okay, we can say at the top of the loop the car just remains in contact, the value of the normal should be equal to 0. So we can say the car remains in contact for value of normal is equal to 0. So we substitute normal is equal to 0. We are going to get this as our mg is equal to mv square upon r, and mass cancels out. So from here we get that the velocity of the top of the loop, that is at point B, is equal to g times r. Now we can use the energy conservation. Energy conservation, which means total energy at A should be equal to total energy at B. Energy at A, because the car starts from the rest, will be entirely potential energy. Okay. Therefore, we can say that we are going to have energy at A will be equal to our mgh, and energy at B will be potential as well as our kinetic. And our kinetic, we know that its velocity is our v square, and the height is our, that is a diameter, that is 2r. So this comes as our mg times 2r, and here this mass cancels out throughout. We substitute value of this v also, therefore we get that our g times h is equal to half, and the velocity was our gr plus twice gr, and we can cancel out this g also. Therefore we get that our h will be equal to 5.2 times r, and this height h is from the, this is the total height h, and we are asked what will be the height above the top of the loop. It means we are interested in this side. Okay, let us call this as our b prime. So we are interested only ab prime. Therefore we can write that our ab prime will be equal to total height h minus 2r. So this comes as 5r upon 2 minus 2r, and giving us r upon 2. So it means above the top of the loop, the height with which from which it should be, the car should be coming, so that the car remains always in contact with the loop, is our r by 2. Okay, so this height is our r by 2. So this is our first question. Now we come to the second question. In second question, it states that a hemispherical ball of mass m rests on the table. The inside surface of the ball is frictionless, while the coefficient of friction between the bottom of the ball and the table is mu, which is equal to 1. A particle of mass m is released from rest at the top of the ball and slides down into it, as shown in the figure. what is the largest value of ratio m is to m for which the ball will never slide on the table. So basic figure is given to us. We are having a hemispherical ball and whose mass is given as m, and we are having, you can see, a particle whose mass is our small m. There is no friction between the mass m and the ball, but there is friction between this mass and the table, and the value of this friction is given to us as 1. Okay, value 1 doesn't mean that it is basically having a friction. Okay, so we have to keep this in mind. And okay, once again we can just consider a position of this mass, and for that let me redraw this figure. Suppose this is the ball and we have this is the center of the ball and its radius is suppose given as r. Okay. And initially we have particle and that is at the top of this ball. Suppose after some time the ball, this particle m is at this, sorry what that, okay, so after some time, let us suppose the particle is at this position. So it starts from point A and now it, after some time, it is point B, and this point B is, let us suppose, is at an angle of theta. Okay. Therefore we can say that the vertical drop of this will be equal to our, because this is our radius, so let us call this as a prime. So we can say our a prime b will be equal to our r cos of theta, and the total height of point A is nothing but our radius r. And at this point B, let us assume that the particle is having velocity v. Okay. So this is the basic thing, and here we are going to use basically the conservation of energy. Okay. So energy conservation, and which means that energy at point A will be equal to energy at point B, and energy at A is entirely the potential energy. Therefore we can write this as our mgr, and that will be equal to our loss of energy at point B, and which we can write as our mg, and this comes as our r cos of theta plus velocity is v, so this will be half m v square, and this mass cancels out throughout and we can combine these two terms. So from here we get that g, we can take gr, we can take as common. Okay. So we got this as our gr 1 minus cos of theta, and we can multiply it by 2, so we get this as our velocity. Okay. So this is our velocity at point B. Now we come to the various forces that will be acting at point B. Okay. So let me specifically only draw point B. So this is our point B and this is our ball, and at point B it is point A and this is point B. So in the downward direction we are going to have our mg. So we can divide this mg into two components. This will be angle theta, so we are going to have our mg cos of theta and our mg sine of theta, and also there will be a normal at the point of contact, and that normal will be toward the radial, you can say radial normal. Okay. So this is our normal. And the velocity we know that is our at point B is our v. So we can use the forces on the particle. And we can say that our this radial, we can write the radial equation of the motion. Radial equation, and radial equation is going to give us our radial equation of motion, and that radial equation will be equal to n minus mg cos theta will be equal to mv square upon r. And from here we can write our calculate our n and also substitute value of v, or rather we can say v square. So which we get our n is equal to, this will be our mg cos of theta, and v square is our 2gr 1 minus cos of theta divided by r, and this is also multiplied by our m. And this r cancel with our r, therefore we get that the value of normal will be equal to our mg cos of theta plus mg, one second, okay, we can further solve it. Okay, so let me, so this will be mg and it will be minus 2 mg cos of theta, so we can take as mg as common, and this will be giving us 2 minus cos of theta. So this is the value of the normal. Okay. This horizontal force on the bowl, and we have a normal, and we can divide this normal also into two components. So this angle will be with theta, so we are going to n sine of theta, and we are going to have n cos of theta. Okay, so there is the only motion is in the horizontal direction, so we can easily write the equation for our horizontal motion. Okay, so we can say that our horizontal force on the ball and the horizontal force will be because of our, you can say, the horizontal reaction of the force. So we can write that, or we can say horizontal component of the normal. So you can say the bowl experiences a horizontal reaction force. And that will be equal to horizontal component of the normal force. Horizontal component of the normal force. Therefore, we can write the equation that force on the bowl will be equal to our n sine of theta, and we already know our n, and n is our mg 2 minus cos of theta, and this comes as our sine of theta. So this is our horizontal force on the bowl. Okay. And furthermore, we can solve it. And because we are interested in finding out the, you can say, the ratio when there will be no motion of the ball. So therefore we are going to find out the maximum static friction available, because there is a force of friction between the bowl and the table. So maximum static friction available. And so for that, let us call this as our F max. F max will be equal to our coefficient of friction and the normal because of the table. And the normal because of the table will be the weight of our this. So we are having M as well as this M. So downward direction we are going to have M plus M times G, and we are going to have a normal of the table. So normal of the table will be equal to M plus small m times G. So you can say our normal of the table will be equal to M plus small m times G. Therefore we get that the maximum value of the friction will be equal to a value of mu is our 1, so we can just put it 1, that is M plus small m times G, and this is our maximum value of the friction. Okay. And for no slipping, because the ball should not be slipping or moving on the table, therefore we can say for no slipping we can write that the friction because of the ball should be less than equal to the maximum value of the friction. And we know both the values, substitute them. Friction because the ball was our mg, 2 minus cos of theta sine of theta will be less than equal to m plus small m times g. Okay, now it is simple calculation, and so we can just remove this g and we get the equation, and that equation is our m 2 minus cos of theta sine of theta is less than equal to m plus small m. Okay. And we have to maximize this. So we are only interested in this trigonometric function. Okay, so let us say that we have our f of theta is equal to sine of theta 2 minus cos of theta. So we derivate it and equate equal to 0. Okay. So we get this as a cos of theta 2 minus cos theta plus sine square theta, and we are going to get equal to 0. So from here we get that our this will be our 2 cos theta minus cos square theta plus sine square theta is equal to 0, and we can write this will be equal to our cos of 2 theta. So we get this as cos 2 theta, or we can also do it if we write this as 1 minus cos square, so that will be equal to, okay, so let us do it. So we can write this as about 2 cos of theta minus cos square theta plus 1 minus cos square theta is equal to 0. And this will be giving us a quadratic in cos, so that will be equal to 2 cos square theta minus 2 cos theta minus 1 is equal to 0. Okay. And this is quite simple quadratic, and if we solve this, we are going to get that value of our cos theta approximately. One second. Okay, so we are going to get this let us suppose that our cos of theta is our x, so we get this as our 2x square minus 2x minus 1 is equal to 0. So we get this as minus b is our plus minus b square, and minus 4 is c, and divided by 2a. Okay, so this will be our 2 plus minus 12 upon 4, and we can write this as 4. So this is 2 plus minus 2 square root of 3 divided by 4. So this will be 1 plus minus square root of 3 divided by 2. Okay. And so square root of 3 is 1.7. Okay, so we can write this as our therefore we can say that value of x will be equal to 1 plus square root of 3 divided by 2. I think this got complicated because cos this is our square 1 minus cos square, and this comes as 2 cos square 2 and minus 1. This is correct. 2 minus this, and we have minus b plus minus b square, and minus 4 is c. Okay, this is also correct. It looks good. So you can say that our cos of theta will be equal to 1 plus minus square root of 3 divided by 2. And so we can solve this. So we can write this as our m 2 minus 1 plus square root of 3 divided by 2, and our sign we can write 1 minus cos square theta and divided by 2. And less than equal to m plus small m. Yeah, I think this is okay. So we get this as m, and this will be 4 minus 1 minus square root of 3 divided by 2, and here we get 1 minus 1 plus root 3, and divided by 2 whole square and its square root less than equal to m plus small m. And furthermore we can write this as m, and this will be our 3 minus square root of 3 divided by 2, and we get this as 4 minus, and if we open this comes as 1 minus 3 minus 2 root 3 divided by 4. We are almost done now. Okay. And so we get this as m, this is 3 root 3 divided by 2, and here we having this will be our, this and cancels out, and yeah, cancel out. Yeah, it looks like. So this comes as minus 2 root 3 divided by 4 is less than equal to m plus small m. And okay, so we can write this as our 3 minus root 3 times 2 root 3 divided by 8, and this is minus of m less than equal to m plus m. We almost done now. So if you solve further, it will only waste of time to compute it. So we are going to get approximately this ratio, or we can say m upon capital M should be less than equal to 1 by 3. Okay, approximately should be coming this. So the maximum value m upon capital M max is equal to 1 upon 3. So this is the ratio of these two masses such that this ball never slide on the table. Okay, so ball should not be sliding on the table. Only the calculation part is little bit lengthy, and otherwise this question is comparatively easy. Now we come to the third question, and the third question, from if you read the statement, it looks like the third statement, this third question is somewhat similar to the second question. Okay, let me go through it. So it states that a hemisphere ball of mass m rests on a frictionless horizontal counter. A mouse of mass m drops vertically onto the rim of the ball and then slowly climbs down the inside to the bottom. It is observed that during this process, the ball moves horizontally a distance equal to 1/10 of its diameter. Find the relation between the m and small m and the capital M. So from the looks of it, it looks like the second and third question is same, but here we have to remember that the hemisphere ball is lying on a frictionless counter, horizontal counter. Okay. Whereas in second case, there was a friction between the bowl and the table. In this case, there is no friction. So in the question itself, we mentioned that the ball moves horizontally by 1/10 of the diameter. So this is one major difference between the two. So therefore, and we have to remember all the forces which will be the horizontal forces between the mouse and the ball are the internal forces. Okay, there are no external forces acting on it. Okay, so which basically means that these internal forces is not going to change the overall horizontal motion. Or simplest term we can say that the horizontal center of mass position remains constant. Okay, or we can say the horizontal momentum is going to remain conserved. So we are only going to focus on this center of mass concept in order to solve this particular question. So this is a major difference between the two. Okay. And so we are given that our counter is frictionless. Counter is nothing but our table. We are given counter is our frictionless So from here we can say no external horizontal force acts on the system. No external horizontal force acts on the system. Second point is that the gravity is only vertical, so it means the gravity also is not going to affect the horizontal motion. Okay. You can say that's a quite counterintuitive, so we are not going to discuss that in detail. And the important part is all forces between the mouse and the bowl are internal. All horizontal forces between mouse and bowl are internal. So it means that they cannot change the system's overall horizontal motion. Horizontal motion. Or in short, we can write that the horizontal momentum is conserved. Okay. And means basically center of mass. Okay. So let us, and for the center of mass we need the coordinate system. Okay. So let us, because with the help of coordinate system it is much more easier to solve the question. And we are given a bowl. Suppose this is the bowl and its radius is given as r. So this is a radius r, so obviously this will be its diameter, that will be over 2r. And let us assume, and we are given a table, that is, this is the table on which it is lying, and we assume that the left side of this bowl is the origin. Let us call this as point A, and this is coordinate 0, 0. And the midpoint, let us call this as B, and the our that insect or ant, what it is, mouse. And mouse is suppose on the right side, somewhere here. Okay, so this is the position of the initial position of the mouse, and with respect to this origin, its position is at 2r. Okay. And because it is nothing but our diameter also. Okay. So we consider that the left edge is our origin. Okay. And this is A, and let us call this point as C. Therefore we can draw everything on a straight line. So this is our point A, which is our origin. We have our point B, which is our radius, and which is our mouse C, that is our 2r, 0. Okay. And so at the beginning we know that the center of the hemisphere is exactly at point B. Therefore we can say that initial positions and initial position we can say that our center of the bowl let us call this as our x be 0, and that will be equal to exactly at the center, that is our r. Okay. And we assumed that mouse is on the right side of the rim. Okay. So we can say that our mouse is at right side. So we can say that is equal to x m for mouse initial position is equal to our 2r. This was our initial positions. Now let us find out the final position. And for the final position, in the question it is given to us that the bowl moves horizontally at a distance of 1/10 of its diameter. So we can, let us draw the initial position first. So initially we were having this A, and this was our B, and this was our C. So this is 0, 0, and this is our r, 0, and we are having this as our 2r, 0. And final position we are given that the bowl moves by a distance of 1/10 of its diameter. Okay, so let us assume that this is the new position of the center, that is our B prime, and this distance is, let us suppose, our delta x. Therefore we can say that our delta x, because it is given that 1/10 of the diameter, and diameter is nothing but our 2r upon 10, so this comes as r upon 5. So new position of our this center of the bowl is a B prime, and it is at a distance of r by 5 from B. Okay, so everything will be moving toward the our right side by the same amount. Okay. So therefore we can write that the bowl center final, let us call this as our xb final, will be equal to r plus r upon 5. Okay. So this comes as our 6r upon 5. And we come to our mouse final. And mouse final, the mouse final position is at the bottom of the bowl, okay, and which is nothing but our center of the bowl. Therefore we can say that our mouse final position will be also equal to 6r upon 5. Now we can use our the center of mass condition. We can say that mass weighted position will be equal to constant. So we can say that there is no external horizontal force, therefore we can write that our mass weighted position will be equal to constant. So it means our mass into position of the mouse plus mass position of the bowl is equal to constant. and there is horizontal motion, so we are only taking the our x coordinates. Okay, so we can write this expression, we can divide into two parts. First will be initial center of mass, and we know that our mass is at a distance of about 2r from the origin, plus mass is at a distance of r from the origin. Okay, so this is our equation number 1. And we can write final center of mass, and that is equal to our mass, this is 6r upon 5 plus mass 6r upon 5. Okay. So we can take 6r upon 5 as common. So we get this as m plus capital M, and this is equation number 2. Okay. So here it is constant. So we can say initial center of mass position is equal to our final center of mass position. Therefore, equation 1 is equal to equation 2. So we can write this as m times 2r. mr is equal to m plus capital M multiplied by 6r upon 5. And r we can just cancel out throughout, and we get this as our 2m plus m is equal to 6 upon 5 times small m plus 6 upon 5 times capital M. And now it is quite simple. We simply combine the similar terms. We get this as our 2m minus 6m upon 5 is equal to 6m upon 5 minus m. And this gives us 10. 10 minus 6 is 4. So this comes as 4 upon 5m is equal to m upon 5. And this 5 and 5 cancels out. So we get that our capital M is equal to 4 times small m. And our ratio, we can say m upon capital M ratio should be equal to 1 by 4. Okay. So this was our third question. So we can clearly see the basic language with minor difference between second question and third question. And the difference is only of the friction. So entire solution approach is going to change. Okay. So this completes the 3 questions for today. Thank you.